Hey everyone, in the last video we introduced ourselves to a number of new types of organic molecules or functional groups. They're all listed here. We learned about alkanes, which are essentially organic molecules without functional groups. We're going to actually do cycloalkanes in just a minute. We did alkyl halides, alcohols, ethers, and amines. And then we went on and talked more in depth about alkanes. We learned how to use a system of naming, which we call the IUPAC system, to make up names for different organic molecules, alkanes and branched alkanes so far. Today what we're going to do is we are going to look more in depth about the structures of alkanes and what those structures can do. We're going to look at them in 3 dimensions and look at their movements and motions, and I always think that this is an interesting part of the course. So let's just start off by asking ourselves, if we take a molecule like ethane, right, this is the condensed structure of ethane, how would we draw this if we wanted to represent ethane in 3 dimensions? So far, all we've really done is we've looked at ethane like that in the condensed structure, and we've also looked at ethane in this cauchy structure, which shows all the different atoms, but are either of these structures really representing the molecule in 3 dimensions? And the answer is no, right? There's no really 3-dimensional structure in the condensed structure, and likewise in this cauchy structure there's no 3-dimensional information as well. This makes it look like all of those carbons are planar, and we know that that's not true. What should be the geometry of one of these carbons? Right? It should be sp3 hybridized, which should mean that that's going to be a tetrahedral carbon, right? So what do we do in order to draw something that's tetrahedral? How do we designate that bonds are not in the plane of the paper? You've seen this before, and so what we do is we use wedges and dashed bonds to represent bonds going in and out of the plane of the paper. So let's just draw a structure of ethane. I'm going to slant this carbon-carbon bond up like this in the middle. And I'm going to add a hydrogen here, so these two with just straight lines would be within the plane of the paper. And then we know that we have one bond that is a wedge, is coming out of the plane, is pointing towards you, and another bond that's going back into the plane. In reality, these two bonds, one of them would be right in front of the other, but we skew one to the side of the other just so we can see it more clearly. Alright, when we get to the other side, we can put our hydrogens, but we have some choices. We could put this hydrogen, I'm just going to put this hydrogen out like this, and then what we can do is we can put our wedged bond and our dashed bond, and so this is one version of ethane in 3 dimensions. But is this the only way that we could draw it in 3 dimensions? Okay, the answer is no. I more or less arbitrarily chose to put this bond going in the opposite direction of this carbon-hydrogen bond, but I could have just as well put this carbon-hydrogen bond going straight up like this. So let's redraw it in that form. So here's our carbon-carbon bond. Here's the hydrogen, the wedged bond, and the dashed one. And so what if we put this hydrogen going straight up like this? Right? We'd still have a wedged bond like this, and we'd have a dashed bond like this. So are these the same? Do they look exactly the same? Well, they are the same molecule, but they're different in that what we've done is we've essentially rotated around this central carbon. So these two molecules would be in equilibrium, and they are what we call conformers. Okay, sometimes you might even see them called conformational isomers in the fact that they do have the same formula and they're different, but I don't usually call them isomers because these are easily interconverted. So conformers are going to be molecules that differ only in rotations around single bonds. Okay, so all we're doing is rotating the bond. So I'm going to pause here for a second. I'm going to make a little video and show you this with a model to help you try to understand what this really would look like in 3 dimensions and not just in these drawings on the page. Alright, so we're going to take these structures, which we could call perspective drawings, and we're going to turn them into the Newman projection. So the idea here is we are going to look at this molecule right along the axis of the carbon-carbon bond. So we're going to bend our face down here, we're going to put our eyeball right there, and we're going to look right along that bond. Okay, so the way that we're going to do this, we are going to draw the carbon in front as a dot. Alright? And if I had my eye there, then I would say that this carbon-hydrogen bond would be going up. Right? And then the wedged one would be going out to my right. The dashed line would be going down to my left. So I would have one bond going straight up, one to my left, and one to my right. Okay, so this is the carbon that's in front. Alright, so I'm going to draw the carbon back in green because I had green atoms on my model. The carbon in the back, we're going to cheat a little bit because it would be right behind it. We wouldn't be able to see it. So we're going to draw it a little bit bigger, and we're going to draw it as a circle. Alright, and so then for the carbon in the back, if this one was going up, this is going to be going in the opposite direction, so this one is going down. And then we have one going out to our right, and the dashed one is going back to the left. So we have one hydrogen that goes straight down, one out to the right, one out to the left. And so this is what we call the staggered. Oops. The staggered conformation. Alright, so if we rotate one of these carbons relative to the other, right, I'm going to rotate the back carbon, so I'm going to rotate this back hydrogen down to here, no, not down that far. I'm going to rotate this carbon just to be in line with this hydrogen to be in line with that one, and this to be in line with that one. So we're going to draw, whenever I draw different conformations, I always keep one of the carbons the same, and then I rotate the other one. And we're just rotating it like you were turning off a faucet or something like that. Okay, so here's the carbon in front. Carbon in back, we've rotated these down, so we're going to put them, they would be directly behind these bonds, but what we do is we cheat a little bit and we draw them just off to the side so we can see them. Like this. Alright, so In this case, we have one in front of the other, just like the moon in front of the sun, and we call these the eclipsed. Eclipsed conformation. And remember that these two are essentially in equilibrium with one another. So we could rotate our hydrogens, these back ones, one more, another 60, and we'd get to another staggered conformation. Then we rotate another 60, we'd get another eclipsed. Staggered, eclipsed, we just rotate one relative to the other. Alright, so now that we have these different conformations, we want to talk about their relative energies. So which one of these two do we think would be more stable, or which would be less stable? Right, so what do we think? So which one is which here? Let's just make sure we know. So this is the, on the left is the staggered, right? And this is eclipsed. Alright, so we're wondering which one is more stable than the other. Alright, so the rationale here is a little bit complicated. We used to use a different rationale in some of the earlier editions of the book, I think, which were easier to understand, but perhaps not correct. Alright, so the rationale goes this way, that the staggered is more stable, okay, because of an attractive force. So, remember, I'm going to draw it over here. Remember when we looked at sigma bonds and we were looking at molecular orbital theory. Molecular orbital theory. Remember that we showed a bond forming between a sp3 of a carbon. This is a carbon sp3 and hydrogen 1s. And we drew our molecular orbital diagram like this. As with all of our molecular orbital diagrams, we generated one new orbital that was lower in energy and one that was higher in energy. All right, and so we showed, I didn't really show the phases here, so let's put that in red. We had a bonding orbital that looked like this. We call this the sigma orbital. And we had an anti-bonding orbital that looked like this. That had a node right between the two atoms. Okay? So in this rationale, we're going to use the sigma and the sigma star orbitals to help our explanation. Alright, so what's going to happen here is if we look at one of the carbon-hydrogen bonds, we're going to look at this case for the sigma orbital. And this orbital, remember, this is all one orbital, has 2 electrons in it. Okay, and here's the other 2 hydrogens. Now the other carbon has its hydrogen over here, right? And the first one is going to donate some electrons into one of the orbitals for the other carbon-hydrogen bond. But the sigma orbital is already filled, and so the only orbital that it could put electrons into would be the sigma star. This is the only empty one. Remember, we always start with 2 here, and we put them into this orbital. Right, so let's draw the sigma star. So the sigma star is going to have like this, and then this orbital here. And then we're going to have, here's our other hydrogens. Alright, so what happens in this rationale, or this explanation, is the filled pi orbital, right? That's over here. The filled pi orbital is going to donate some electron density into this empty pi star orbital. So we're going to get some orbital overlap and some sharing of electrons. Oops. Sharing of electrons from the sigma orbital of one carbon to a sigma star orbital of another. All right? And this can happen for every pair of carbon-hydrogen bonds around here. This whole process is referred to as hyperconjugation. We're going to use this again later on for a different situation. But so there's an attractive force, which is only felt when the molecule is in the staggered conformation. When it's in the eclipse, those orbitals don't overlap. All right, so the staggered is more stable because it has this attractive hyperconjugation going on. If we look at the energies when we rotate from one conformation to another, we can graph it out. So in this case, what we're doing is we're looking at the angles between these two hydrogens here. This is referred to as a dihedral angle. So the angle of one bond on one carbon to the bond on another carbon. So in our starting point, almost our starting point, we have a 0 degree dihedral angle. So is this conformation, is that staggered or is that eclipsed? That would be eclipsed, right? All right. As we rotate the back hydrogen down, the back one's going to rotate here. It's going to come down to here. After we've rotated 60 degrees, we come to a staggered conformation. Right? And so the energy goes from a high point when it's eclipsed to a low point, or an energy minimum, when it's staggered. If we continue to rotate, we rotate this one down like this, that hydrogen is now eclipsing the next hydrogen over. So after 120 degrees, we're eclipsed again. If we keep rotating it down, we get to another staggered, and so on. We go alternating between that staggered, it goes to eclipsed, we go to another staggered, and this comes up here back to our starting point. All right, so notice we end up kind of with this wave of energies where all of the staggered conformations are lower in energy and all of the eclipsed conformations are higher in energy. So the energy difference between these two, so the delta E between staggered and eclipsed, is about 2.9 kilocalories per mole. Okay, and the way I think about this then is that it's about 3, right? About 3 kilocalories per mole. And this is about 1 kilocalorie per mole for each eclipsed pair of bonds. Okay, so this is the amount of energy that's being spent when we don't have hyperconjugation. Right? We rotate it by 60 more degrees, we gain that energy back. So this is a pretty regular energy diagram though, right? All the staggered conformations are the same and all of the eclipsed are the same. So what happens if we add another group onto our structure, we make it slightly more complicated? All right, so in this drawing, what we have is we have the conformations of butane. So let's just look at butane. So we have a possibility of having, let's draw the starting point here. We're looking at this center bond, right? And we're starting out in this conformation right here. Okay, where we have the two methyl groups up here in the same plane. All right, so we have a 0-degree dihedral angle. So now what we're going to do is we're going to rotate again the back. This time we're going to rotate the front carbon and we're going to keep the one in back constant. All right, so we're going to rotate this methyl over here. Right, so we go from a eclipsed again to a staggered to an eclipsed to a staggered, eclipsed, staggered, and back to eclipsed. All right, we've just done 360-degree rotation. All right, so let's look first at the eclipsed conformations. So here's one, and here's one. And then we get back here. This one's the same as what we started out with. So would these three eclipsed conformations be equal in energy? Well, you can cheat a little bit here by just looking at the graph, right? Notice that here's A, right? That's this one right up here. And C, right here, those two eclipse conformations are at different energies, right? So why is that? All right, so when we push the two biggest groups, when big groups are pushed close together, they start to bump into each other. Okay, so remember each of these have methyl groups out here, whoops, like this, and they're going to start bumping into each other. I'll make another video on the next slide to show you how this looks. And when they start bumping together, they repel each other. So the electrons around the atoms start to repel each other. And this is called steric strain. And the steric strain raises the energy. So conformation A is higher in energy than C because the two methyl groups, the two biggest groups in the molecule, are being eclipsed and being pushed close together. That creates more steric strain and makes it less stable. All right, so now compare C and E. Look at those two. They're at the same energy. Why would that be? So the reason that they're the same energy is if we look at their structures, we notice that each methyl group is eclipsed with a hydrogen in this structure. So each methyl has a hydrogen eclipsed, and that's the same situation in this molecule over here in E. So both of those are exactly at the same energy. So we have one that's higher and two that are the same. All right, so now let's look at the staggered conformations. So here's staggered. This B is right down here. we have a staggered, which is D, and then F. D and F. So like before, notice that all of the staggered conformations are lower in energy than the eclipsed conformations. But we have one staggered conformation, D, which is the lowest of them all. All right? Notice that B and F are the same, and D is the most stable. So why would that be? So let's compare B and D. All right, so here's B and here's D. Let's look at their two structures. Okay, so in B, notice that the two methyl groups here are only 60 degrees apart. All right, whereas in the most stable conformations, the two methyl groups are opposite of one another at 180 degrees apart. So the most stable conformation is the one that puts the big groups the farthest apart, which minimizes this steric strain. All right, we have names for these two conformations. When we put the big groups opposite of one another, we call it anti. Okay, so that means opposite. And when they're 60 degrees apart, we call it, it's kind of a weird word, we call it gauche. That's how we pronounce it. This is 60 degrees. And this is 180. All right, so gauche interactions create some steric strain. Notice if we look back over here to F, we notice also that these two methyl groups are 60 degrees apart, so this also has a gauche interaction between those two, and so F and B are at the same energies. As we build more complicated molecules and we want to analyze them, we may have more than one gauche interactions, or we'll have one that's staggered and one that's gauche. In general, we want to put the biggest groups, the biggest substituents, far apart. All right, so let's just work our way through one more structure, and this is something that I will ask you to do on an exam. So we're going to look at the conformations of 2-methyl butane. So let's just start out by drawing that off. Here's butane, and it has a methyl group at position 2. Right, so we're going to look at the C2C3 bond. Okay, and what we're going to do is we're going to draw two structures. One is going to be the most stable, staggered. Well, we know the most stable is going to be staggered. And we're going to also draw the least stable, eclipsed. Okay? So how do we approach this? So what we want to do is look at this molecule along this bond here, because if we count it 1, 2, 3, it's along the C2C3 bond. Now what I find the most helpful when I do this is because the carbon 2 and carbon 3 are tetrahedral, let's go ahead and draw all of the bonds in and use wedges and dashed lines to show the bonds that aren't within the plane of the drawing. Okay, so I could make this methyl group either be a wedge or a dashed line. It'll work either way. So I've just arbitrarily chosen a wedge. Okay, so this is a CH3 here. I'm going to draw these in. This is a CH3 here, and then I can't really fit it in. I'm going to put it in over here then, is an H. Now this brings up one comment, is when I'm drawing these wedge and the dashed bonds, I always skew one to the side of the other just so we can see them. But there is really no rule about which one is skewed to the right or the left. So it doesn't have to be that the wedge is to the right or the left of the dashed line. We just have one skewed next to the other. Okay, so that's around one carbon. And then what do we have at C3 that we need to still draw in here, right? We're going to have a wedged carbon-hydrogen bond and a dashed carbon-hydrogen bond as well, and this is going to be a methyl group. Okay, so I'm going to put my eye down here, and I'm going to draw just what I have. Okay, so remember the carbon in front is with a dot. We're going to have a methyl group up like this, so that's going up to 1. The wedged bond is going to be going out to my right, so that's over here, and then the dashed bond is over here, and that has an H on it. Right, so that's the carbon in front, so that's carbon 2. Now carbon 3, remember, I'm going to draw as a circle. We have this carbon-carbon bond is going opposite direction of the first one, so it's going to be going down. Right? And then we're going to have the 2 hydrogens going up to the right and to the left. All right, so this is, what is this? Is this staggered or is this eclipsed? Okay, so this is staggered. All right, now, so what we want to think about is whether this would be the most stable of the staggereds. So let's just rotate one of these around. Let's keep the carbon in the front the same, and I'm going to rotate the back one. Rotate back by 120 degrees, right? Because we're going to go from one staggered to another. All right, so this H is going to rotate down to here. This methyl is going to rotate to there, and this H is going to rotate over there. Okay, I'm going to keep the carbon in front and its groups just the same. Always keep one the same and rotate the other. All right, so now our methyl group in the back carbon right here is going to rotate up to the left, and then the 2 hydrogens are going to rotate as well. So this methyl group goes here, this goes here, and this goes here. Okay, so here's another one. Let's do one more just to be complete. Okay, so we're going to rotate another 120 degrees, and so this methyl group is going to rotate over to where that H is. This H is going to rotate where that H is, and this H is going to rotate over to where that methyl group is. So let's just do it again. Front carbon is the same. Back carbon is rotated, so now I have a methyl group here, and then an H here, and an H over here. Okay, so these are the 3 possible staggered conformations around a C2-C3 bond of 2-methylbutane. So let's rank these in energy. Okay, so let's say first which one is going to be the highest in energy. All right, we're going to give this a number 3, highest, worst. Okay, or we'll just say it's the highest. So which one's going to be the highest? All right, so let's notice what types of strain we're going to have here. So for the first structure, we have these 2 methyl groups right here, and these 2 are gauche. And remember, that creates some steric strain. All right. The other 2 groups, this methyl group and this methyl group, these 2 are anti, so that's a good situation. All right, let's look at the next one. We look at all the interactions, and here again we have this interaction, 2 methyl groups 60 degrees apart. This is also a gauche interaction, so there is some steric strain from that. Okay, no other gauche interactions. So now let's look at the last one. Okay, look at here. There's a gauche. Oh, and look, there's another gauche here. So this one has two gauche interactions. So this is the least stable. And these two are the most stable. They're equally most stable because they both have just a single gauche interaction. All right, so we could draw either of those to get our answer here. So either of these two would be most stable. Okay, what about the eclipsed? All right, so I'm going to keep the front carbon the same again. And what I'm going to do is I'm going to take that structure up on top and I'm going to rotate it by 60 degrees. Okay, so which way do I guess I'll draw all of these out again. So remember the one in the back is a circle. So we're going to have an H here. We could have CH3 here and an H over here. Okay? Make sure when you draw these that we can tell which bonds are going to the front carbon and which ones are going to the back. Alright, so in this case, we have all of the CH3s are just eclipsed with other hydrogens. In fact, every CH3, there's two of them in front, that one and this one, and there's one in the back, and they're right here. Each hydrogen is just eclipsed with another, with a methyl group. Okay, so let's rotate. We're going to do, again, the back carbon by 120 degrees. Let's see if I can fit this in here. I'll put it over here. CH3. Here's the dot for the front carbon. CH3. H. The back carbon. All right, so we're going to rotate this H over here. So that's going to put an H down here. Let's see, another H is going to rotate over to this side. And our methyl group, this one down here, is going to rotate up here. So our third bond is going to be a CH3 right here. Okay, so now in this one, notice that we have a lot of steric strain right here because we have two methyl groups eclipsing one another. We didn't have that in the first one. Okay, let's do this one more time just to be complete. Remember, we keep the front one the same. And then we're going to rotate the methyl group over here, H over here, and an H over here. Okay, so what about this one? How does this look? Well, we got a lot of steric strain right there. So which one of these do you think would be the most stable? Okay, so the most stable would be this one on the left. And what about the least stable? That's where we're actually looking for. Would be the same for these other two. So these two, either one of them in this would be the least stable. Because they're both equally unstable. They both have one situation where the big groups, the methyl groups, are eclipsing one another, creating a lot of steric strain. All right? So, when you have this type of problem, it's important to take it one step at a time, right? So the first thing we did, remember, was that we drew out our structure and we drew all of the bonds attached to the two carbons that are going to be involved in our Newman projection. So we were doing C2 to C3, so we wanted the bonds that are in the plane, the wedge, and the dash on each one of these, right? And then we're going to draw our first Newman projection, and usually I just draw it whatever I drew right here, all right? And then we can look at it and we can decide, is this the most stable, if that's what we're looking for, or not, all right? If it's not, then we can do a rotation and try to come up with the least stable, and so forth. All right, so that's the end of this this video. Okay, so what we've learned this time is about the dynamic nature of alkanes. Single bonds can easily rotate around one another. This 3 kilocalories per mole that we talked about, the energy that's the difference between the eclipsed and the staggered, is easily obtained at just room temperature for molecules. So they are almost spinning freely, but they have more favored conformations, which are all of the staggered and the ones that put the big groups far apart.